Hey guys, how's everything going? This is JSer, who is not good at algorithms. In this video, I'm going to take a look at 144 binary tree pre-order traversal because I'm a front-end engineer, and there, we have a lot of tasks to do with the DOM, right? DOM, manipulating DOM traversal, and DOM is actually a tree. So I want to spend some time on all the tree traversal problems. Okay, about the inorder travels, I've already done it before. It's 994. Please search on my channel for that. And in this video, I'm going to take a look at pre-order. Okay, so we're given a tree like 1, null, 2, 3. We need to return 1, 2, 3, right? Like, okay. So, yeah, so pre-order means the root must be first collected, like root left right, right? So the root left right order. If you still remember how we do in the inorder traversal, you know that actually pre-order is a little easier than the inorder traversal because this actually the order we step on the nodes is the order we collect the nodes, right? We step on one, and then we can collect this result. So we step on one, step on two, and step on three, then the result 1, 2, 3. But for in order, it's not. In order is left, root, right, right? So when we are step on one, we don't know where the left is, so we go step on its left, but there's might be still left, so we step on find the leftmost left node and then collect, right? So the order is not how we step on the node. I'd like to separate the tree traversal to two phases, two processes. The first one is walk. So suppose there's a little man step on the root, and now let's think how it will move around the graph, move around the tree. But there is another basket in his hand. He like to collect the result, right, in some order. So if a pre-order traversal, he step on one, then he can directly collect the result, and then the next one would be you go to left and then go to right, go to left, and they still left, then they go to left, right? So for each node, it will step on the root and collect the result, and then go to left, collect the result, and do that recursively. And if it is an inorder, it will step on one, but he will not collect the result. He will step on the left, right? First, step on it, and then collect the result, right? Yeah, cool. So let's try to implement it. The first idea, of course, is recursion. Let's create a walk method. The accepts a node as a parameter, and another one is a result. So when this function is done, we will return walk root this, right? So now when we step on a node, as we analyzed here, 1, 2, 3, right? We get the node, we collect the result. Of course, if node is null, we do nothing, right? We do nothing. And if it's not null, what do? We collect. So result will push the node val, and then what? We step on the left node, right? So walk node left, and then walk node right, and step on left, and then if it's not null, we go step on left. So yeah, it's what we want. Let's try. Ooh. I'm sorry, I forgot to pass the result. At last, I need to return result. Yeah, I think we're good. Let's submit. Yeah, and now The time and space, of course. The time, it's linear. It's for all the nodes. Space, there's a call stack, right? So the max height of this tree, max height, height, tree height. So worst, it's linear. Now let's try to rewrite it in an iterative way. Iterative is very simple. Just like we did it here, we walk and then we walk and then we collect, right? So we first, of course, this is a DFS. So we use a stack. We put a root in. We first put a root in, and then get the root, pop the root, and collect the result, and then push right and left in, right? So now we can handle the left again, and then, like you see, if it's possible, it would be left, 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 right? Or something like right, right, left, left, right? Cool. So this is what we want. Let's create the result and the stack. Stack will be root will be default in it. So our iteration will continue while the stack is not empty. We pop the top node. And finally, we need to return the result. Because top equals stack top. So if it is null, we do nothing, right? So continue. And if it is not null, what we do, just like we did here, we collect the result. Push top out, and then result. Remember, we need to write before left, right? So we push right, which is top right. Not a result. My bad. It should be stack. Stack it, then push top left, and then it's done. So try it. Cool. Yeah, it's still accepted. The time and space. The time, yeah, it's the same linear time. For space, well, actually, it's the same. Here is the call stack, but here is actually a stack of all the path. The right node actually. So if we put one, it will stack the right and left, and then right. So for deepest path, the corresponding right nodes list of the deepest path. So it's still worst case is linear time. So that's all for this problem. I want to address that for a tree, different tree may have the same preorder. So you see that for one null 2 3, we got 1 2 3, right? 1 null 2 3, we got 1 2 3. But if we got 1 2 3, like 1 2 null 3, it's still 1 2 3, right? Or there's a null here, it's still 1 2 3. 1 2 null. I'm sorry, there's no null here. Oh, so actually this what is the 1 2 null. I see. Actually, LeetCode uses the BFS format. BFS to construct the tree. You see 1 2 null 3. So if you want to put a 3 here, it should be 1 2 null 1 2 null 3, right? Yeah. So even for this one, it's still 1 2 3. So if you just get the one array of the inorder traversal, we cannot construct a tree. It's not unique. So that's what I want to say. Okay, so we still have a little time. Why not we just retry, just do the inorder traversal, not try inorder traversal. Okay, so let's construct a tree called 1, 2, here's 3, and then null 4. Oh, 1, 2, 3, null 4. Oh, there's no space, I think. Okay, 2, 3, null 4. Okay, 5, 5, null, and null 6. Okay, this is the tree we're gonna take, and let's try to do it with inorder traversal. First, we will do it in recursion. It's the same, basically the same. Remember, when we get root, we need inorder. We should be left root right order, right? So when we walk on a node, if it is null, of course we do nothing, and we return the result. And now, like this, we walk on 1, but now we shouldn't collect it. So we continue walking 2. We cannot collect it. No, we can't collect it because there's no left node. You see, there's no left node. And then we will collect 2, and then 4, right? Collect the right, and then come back to 1. Okay, so the recursion should be, we walk 1, and then because it has left, we walk to left, and then there's no left, and then no left, so we collect this result, and then there might be 4, right? So there still might be 3 here, and then we walk on 4. Okay, so you see the order, we just need to modify the order a little. I think it's like this. We walk, and until the last one, at 2, we cannot walk to the left, right? It's null. We return, and now we collect, which is 2, and then we go to right, and then when this tree is done, so the walk for this node is totally done, and then we collect 1. Yeah, so that's it. Let's try to run the code. So we output 2, 4, 1. Let's see if it is right. Not diff, but the tree. Oh. Okay. So it should be null. No, it's 2, 4, 1, 6, 5, 3. So yeah, that's it. So we just need to change 1 liner to modify the order here. Okay. Now, what about inorder traversal for the preorder traversal? For the stacked. Okay, now this is a little more complicated than the preorder traversal. If we got a root, and then what we get, remember the push stack, the element is pushed to stack, is actually a walk, right? But now we only collect the result when we pop the element. For inorder traversal. So when we get root, we need to collect it later. So we still need to push root in, right? No, not push root, but push right in, and then push root, and then push left, right? And what's the next one? Next one is we get left out, and we push right root, and then like the tree here, we push one in, push 3 in, 1 in, and then push 2 in. Now we handle 2, but still we need to push left in it, and left no, it should put right in, and then root, and then left, right? So the old stack should be 3, 1, 4, 2. Left is null now, so 2 null, right? 3, 1, 2, 3, 1, 2. Yeah, this is left, so it should be this order: left, root, right, and right, root, right. Yeah, do something like this. When we're using a stack, we need to push the elements in the stack, but we push it. So we get 2. If there's another node here, we need to handle that first, right? So we got to for 2, 1, 3, it will become like here is 7. So it was 7, 2, 4, and then 1, 3, right? Okay, so there's a stack like this. I'll create a push stack function, which is node. So when it push all the left node in it. So while node is not null, stack push node equals node left. Actually, this is the collector, the result order. In the stack, it's not like this. It's actually, it should be in the stack. No. In the stack, it should be 1. We got 1 root. Okay, root. We push root, and then left, and then still continuing left, right? Now when there is no left, like 2, we collect this node and push it right, left in if there is. So it's still root, left, left. It's kind of like right and then left. Well, we should explain this with the root tree. Okay, we push stack. So we push root in. Okay, now we start popping, right? We first we'll push 1, 2 in it because one pushed in it. Now we should collect the result. Okay, we pop. If it's null, we just continue. There should be not null in it, so there's no need to check this one. Okay, we pop it. We get the first one with no left node. So it's 2. We connect the result. Result push top val. Okay, then we'll start working on its right? So we push stack top right. This is what we'll call the function recursively. You push 4 in. Okay, 4 is in the stack. And now 4 is the last one, so 4 will be popped, and then we go to 1, collect it, and then pop 3, and push 3, push 4, 5, push 6, and then collect it. 3, 6, 5, 3. I think this should work. Let's try. We got 2, 4, 1, and then 6, 5, 3. Yeah, that's it. So that's all for the